We're here with Pieter Tans, one of the scientists here at what is the technical name for this facility?
It's NOAA's. Well, no, do people know what NOAA is? Maybe not.
Oh, I know what NOAA is.
Yeah, but I mean, the general public?
Oh, okay, all right.
The Earth System Research Laboratory.
Okay.
Part of the National Oceanic and Atmospheric Administration.
Okay, all right. Very good. All right, so obviously you're very involved here in data collection. A lot of the gases that are the primary culprits when it comes to climate change. Talk a little bit about the consciousness of this facility in terms of how seriously you take this work and the amount of quality control that goes into it.
So every measurement that we make is very carefully calibrated with reference gas mixtures. So every instrument that we use is calibrated many times per day by different reference gas mixtures. So now it responds to a particular concentration of a greenhouse gas. And then we compare that with the response of the instrument to actual air sample. And then we can take the instrument's response and put a number on it, what that means in terms of concentration. And we do that day in, day out. So everything depends very strongly on how we maintain our reference gases.
Now, when you say reference gas, what does that mean?
A reference gas is a mixture of an air-like mixture, so it's CO2 in air, or methane, another greenhouse gas, in air, nitrous oxide in air, natural air, that we have pumped up in a clean air environment and modified the concentration of the greenhouse gas in question by a little bit, either decreased it or increased it. Then these form the basis of our calibration scale. And this calibration scale is propagated not only to all of our measurements, but also to other people. So our measurements, our calibrations form the basis of the international greenhouse gas measurement system that is coordinated by the World Meteorological Organization. But you could say, well, why should I believe these reference gases? Because we make them and we maintain them. Well, there's many different ways in which you can create a reference gas mixture. A reference gas mixture, it has a very well defined, very well known concentration of the greenhouse gas that you are trying to measure. And we know that by creating these, from first principles, from very basic measurements, we get to know what the concentration is, and then we propagate that. Well, there's other laboratories in the world who also make reference gases via different methods, completely different from us. And we compare, and we all get the same answers. So we compare with very many different labs who actually make calibration gases. Mm-hmm. And so NIST, National Institute for Standards and Technology, for example, they have their own reference gas mixers, and they agree with ours to very great accuracy. So we can really have some faith in that right. We're looking at reality here.
We had talked earlier about some would say that carbon dioxide is a trace gas. It's less than 1% of the atmosphere. Why should we be worried about that? And what would the world be like if we didn't have the amount of CO2 we had in the air even before the Industrial Revolution took place?
Well, there have been episodes in the Earth history where the Earth was a frozen ice ball, at least the surface of the Earth. Most of the oceans were frozen over, and CO2 was very low during these times. And the Earth got into this state. And it was very hard for the Earth to climb out of this, because once it's all white, it reflects a much larger fraction of solar radiation than it does now. Mm-hmm. And so it can't get out of it. But CO2 actually did get the Earth out of it. This is about 700 million years ago. There was still volcanism ongoing. I mean, the volcanoes would erupt, regardless of there was a thin layer of ice at the top. That didn't matter. So CO2 was coming out of these volcanoes, and over millions of years, very slowly, CO2 built up, and it was volcanic CO2. Until at some point it was high enough, many times higher than it is today, by the way, to heat the Earth up through the greenhouse effect, regardless of the fact that the Earth was covered in ice. Mm-hmm. And then at a certain point, the ice started melting and the Earth got darker because and immediately went from a very cold Earth into very hot Earth. So from the ice house into the hot house in a geologically very short time. This is very well documented in the geologic record.
Gotcha.
So that's what you get with no CO2 or no greenhouse gases. The Earth will be an ice ball.
Another counter argument that I hear is that, well, water vapor is a greenhouse gas, and there's way more of that than there is CO2.
True.
And so if we're not worried about water vapor, why are we worried about carbon dioxide?
See, water vapor has a very short residence time or lifetime in the atmosphere. Typically, all of the water vapor that enters the atmosphere, mostly through evaporation from the ocean surface, tropical oceans in particular, stays in the atmosphere for about a week or so before it condenses as rain or snow at higher latitudes or higher altitudes and falls back out. So typical lifetime is about a week. Well, the lifetime of CO2 is very long. The turnover time of CO2 in the ocean atmosphere system is of the order of hundreds of thousands of years, actually. And so CO2 hangs in there. And what water vapor really does, the amount of water vapor in the atmosphere depends on the temperature of the Earth's surface itself. So if the ocean surface is warmer, there's more water vapor. Just, when you have a pan on your stove and the water is lukewarm, there's a little bit of vapor coming off. But if you really heat up the stove, before it gets boiling, the water vapor that's coming off is much, much more than at a lower temperature. And also for the oceans. If the ocean surface is warmer, then more water vapor is being injected into the atmosphere. And so, what water vapor does, it amplifies the effect of the long-lived greenhouse gases. But it itself doesn't have the staying power to make the greenhouse happen.
Right.
It's the other greenhouse gases that it amplifies. I'll give you an example of how much water vapor actually is injected into the atmosphere. We currently emit about 10 billion tons of carbon per year in the form of CO2. Well, natural evaporation of water from the ocean surface is about 500,000 billion tons. 500,000 versus 10. So, we emit water in our tailpipes too, from cars, for example. Of course, it doesn't play any role whatsoever compared to how much water vapor the oceans always put in the atmosphere. So we see water vapor as part of the climate system itself.
Right.
It is not something that is really controllable. The Earth temperature itself determines how much water vapor there is. If it's cold, there's a little, and if it's warm, there's a lot.
It almost reminds me of a guy that tried to do a story about, there are correlations that looks like something's causing something else, but it's not really true. And what he did was he said, well, gee, it gets cold every fall, and that's about the time people start playing football. So he theorized that football caused winter.
Yeah. Good luck.
Just trying to show the absurdity of that.
Yeah.
Okay. So the ice core records show CO2 and temperature oscillating over millions of years. There have been arguments made that in those ice core records, the temperature increase appears to lead the CO2 increase. And so during all those cycles, CO2 was not forcing temperature, so what makes this different?
First of all, it's good you say appears to lead.
Okay.
Because we don't know, actually,
okay.
if that is really true. In a very high resolution, so you go back 800,000 years with ice cores. And the ice cores registers the ice core registers CO2 concentration, but also the temperature in the middle of Antarctica, for example. That itself may lagging something else, like global temperature, or leading it.
Okay.
So we don't know if that is really true.
Okay.
Anybody who claims that is true doesn't know, really.
Okay.
So we as scientists don't know which leads or lags. What we do know is that greenhouse gases will cause warming. They will retain heat in the atmosphere. This is known from elementary physics, right, and was already known in the second half of the 19th century. Was already known, and the knowledge got better and better through the 20th century. And by the time quantum mechanics was invented in the first half of the 20th century, people like Schrödinger and Einstein and all those people, their understanding of absorption of infrared radiation by certain gases became better and better. So this is really understood. Right. No question about it. Then we also know that climate itself can cause CO2 to rise or drop. That's possible.
Okay.
And that's because the amount of CO2 in the atmosphere depends on ecological processes, on ocean currents overturning, like upwelling in certain regions, deep water formation in other regions, and how that is configured, and what the net effect is on the atmosphere depends a little bit on climate itself.
Okay.
What is the circulation at a given time? Is more water exposed with high CO2 in the oceans to the atmosphere or less? I mean, that depends on how the ocean circulates.
Okay.
So we know that CO2 has an effect on climate, and we also know that climate has an effect on CO2. Both are known. Well, perhaps we have a recipe here for a feedback effect, where one feeds on the other. So climate might get a CO2 increase started, but then CO2 will cause more, say, climate change, a little warming, because ocean currents are a little different at a given time, for some reason, difficult to understand in detail, often. Then that CO2 will cause more of the same, and so will feed back on itself.
So that's a positive feedback.
Yes.
Can you foresee in your wildest dreams any negative feedback that could end up counteracting all of this?
Yeah, potentially there are some negative feedbacks. For example, a warmer surface temperature because of greenhouse gases might lead to more low-level clouds, for example, which would produce cooling.
Okay.
Has not been observed, by the way, but that's possible.
In theory.
In theory, yeah. We don't know this.
Right.
Could it? But I stick with what's been observed so far.
Right.
And what has been observed is with the warmer ocean, we have more water vapor in the atmosphere. That's a positive feedback. Positive feedback meaning makes the situation somewhat unstable. Positive feedback means that what happens makes the cause of what happened even stronger. So it feeds back on itself. You get more of the same. And so positive feedback, when people talk to each other, sounds like a good thing. I give you positive feedback, right? I like what you're saying.
Right.
No, this is a different kind of positive feedback. Okay. This is in an engineering sense, an Earth system sense. Positive feedback typically leads to some kind of an unstable situation.
So positive feedback leads to amplification.
Amplification, yeah. So we do know also, I would say, from the geologic record that at some point negative feedbacks probably do kick in, although I don't know what they are, because you look at the last 800,000 years from the ice core records and you see that there's these high periods of CO2 and high temperature and low periods of low CO2 and low temperature. But it's almost like it was like a rail, like it went from the low point to the high point and then stopped going up and then came back down again. It's like some positive, some negative feedback was limiting the response somehow. But a 5-degree change between ice age and interglacial, the Earth looks like a different place. So 5 degrees centigrade is a lot for the global average.
And there are a lot of people that will say, well, I've experienced, in this case, a 9-degree Fahrenheit increase.
Yeah.
That's not a big deal. We do way more than that just on the annual cycle. But a global average, like you said, is very different.
But now we're moving in the other direction. You see, I was talking about the last 800,000 years. Now we're going in a different direction, for which we don't have an analog like the ice ages. Because we can see in ice ages and the interglacial that sea level rise went up and down by very large amounts. Even today, if we were to melt all the ice on the Antarctica and Greenland, sea level rise would go up about 100 yards. No more New York City.
Right.
So the question is, of course, how fast would this happen?
Right.
We don't know that either. But we do know from the geologic record that these periods of sea level rise have been there and have been sometimes been fairly rapid. Of the order of a centimeter per year stands in my head as I read somewhere our paper.
So that leads me into
Yeah.
the next question then, is
Yeah.
that there still is, there's a lot of certainty, but there is still some uncertainty about feedbacks and so
Yes.
forth. But is the best way to look at this issue risk assessment, where no, you can't say that everything is pointing toward this happening, but a lot is, and do you want to roll the dice and take a chance? Is that
Yes.
a fair way to put it?
Yeah, that's the way I look at it, actually. I compare it a little bit with playing Russian roulette. So, you have a gun, 6 places for a bullet. I got only 1 bullet in there and 5 empty slots. Let's pull the trigger because there's only 1 in 6 chance that it will kill me. Mm-hmm. There's some analogy to that. Because there is a finite chance, finite meaning maybe 1 in 10, could be 1 in 5, could also be 1 in 20, of catastrophic climate change that will have some positive feedbacks that are poorly understood at this point. It might really put us in a different climate state in a relatively short time. And that would mean, of course, tremendous stress on society, to put it nicely. Mm-hmm. And that's my analogy with the Russian roulette thing. Maybe there's a 1 in 6 chance that we run this risk. So, to me, it makes eminent sense if we lower the risk and invest in doing that.
Right.
And don't look at it as a cost, but as an investment.
Right. But as you
that's like 2 sides of the same coin,
Right. And you had mentioned to me earlier about that investment could involve an awful lot of people being employed.
Exactly. So we need to revamp our energy system. On the one hand, it's going to cost, so an energy system that is really in the end carbon free. So no more combustion of fossil fuels. We know that much, actually. The science and understanding of CO2 in your system tells us we have to go to 0 emissions. There's no question about that. Mm-hmm. Because the buildup of CO2 in the atmosphere is cumulative. It doesn't matter in the long run whether we take 1,000 years to burn a certain amount of carbon or 100 years. In the end, the atmospheric concentration is pretty much the same. So it's cumulative and the emissions have to go to 0. Well, that's a big job. And it's going to cost an awful lot of money. But at the same time, it means we're paying for an awful lot of jobs making this transition. Mm-hmm. So we can see this, trying to solve this problem, you can look at it as basically an economic stimulus program.
Gotcha. What do you make of this 17-year quote-unquote hiatus of the warming after the 98 El Nino? The rate of increase has been pretty negligible. A lot of people use that argument as, well, the CO2 has kept going up, global temperature hasn't, end of discussion.
I find that a very silly argument because there is, of course, more retention by greenhouse gases, and we can see the increase in temperature in the last several decades. Let's say starting from maybe 1970, we could really start seeing this. But you look before in the record and you see ups and downs in global temperature by natural processes. The climate system itself doing its changes over 10, 20-year time spans, oscillating more or less. And that is still happening today.
Right.
Why should we now suddenly only have the man-made impact? The natural system is still there.
Right.
So I'm so totally unimpressed by this argument. Also, it's faulty in a statistical sense, because these people take 1998 as the reference year.
one of the warmest years on record.
Yeah,
Right?
1998 was an exceptionally warm year. So 1999, 1 year after, and 1997, 1 year before, were very different, much lower temperature. Why don't you take those as reference points? It's just silly. You know, from a statistical point of view, if you take a statistics 101 in college, and you do this, you get an F.
Make sure you get that one. Now, there are always going to be advocacy groups for different things. And there are certainly groups that are passionate about climate change not being real, at least not the man-made part. But then there are some that are very passionate about preserving our environment, and they wholeheartedly accept the science. Are there times when those advocacy groups overplay the issue in such a way that it hurts the science community's ability to make the argument?
Yeah, I tell you, from the viewpoint of the public, science's weakest point is that we cannot predict with any degree of certainty what it will look like 20 years from now, and certainly 50 or 100 years from now. And that's because we do not understand these slower feedbacks. See, that's the sad thing. We know that this is a serious problem and it's really going to change the climate, but whether it's going to be much worse in Miami versus Toronto, or we can't, or what it's going to do to the water cycle, to droughts and precipitation, we can't really say with a lot of certainty. And that sort of weakens our case, at least. When you can't not tell people, hey, this is going to happen.
Right.
And people say, oh yeah, you know, it's not my worry.
You see a parallel here with the tobacco issue back in the 70s?
Well,
I mean, where
at a certain point, the evidence for tobacco being bad for your health was very, very clear. And yet, a public relations campaign, very well run, managed to forestall serious limitations on tobacco use for a couple of decades. Maybe 2 decades, 3, but quite a while. And so we also have a very well-run campaign, actually. It's run by the same people, by the way, public relations firms.
Right.
They learned how to do this during the tobacco wars. And they use the same tactics now in the climate change wars. It's a pity. But that's, yeah. So I refuse to be very specific about what it's going to look like, because I don't think I can trust those answers with a lot of confidence. But I do know that the change in the heat budget of the Earth is very serious.
Right.
The amount of extra heat retained over the years is enormous. I just know it will make the Earth look like a different place.
Right.
I just can't say how.
And so, I mean, what I'm taking out of this is that your science is not being arrogant about this. Science is admitting that there are still unknowns, but they're also very, very strong about what they do know. And what they do know deserves a response.
Yeah, so yeah, I can summarize, I think, in a few sentences what we do know with a lot of certainty. First, human beings have caused the greenhouse gases to increase.
Right.
There's zero doubt about that.
Right.
Many, many lines of evidence, completely independent. We do know how greenhouse gases absorb infrared radiation from the Earth, which otherwise would go to space.
Right.
And keep it in the Earth system. We know this we know that with great accuracy. And then we also know that especially the CO2 change on Earth will be with us for a long, long time. We are committing the Earth and future generations to high CO2 for thousands of years. This is known.
Right.
Well, so climate change is a given with these 3 things.
Above and beyond natural.
Yes.
Yes.
Yeah. That's the other thing about climate change. So we can say, look at the last 800,000 years, and we see that climate has gone up and down, and CO2 has gone up and down over, like CO2 varied between 180 parts per million and say 290 or so, during ice ages and warm periods. When you look at one graph, 800,000 years in one graph, it seems like it happens pretty rapidly. Mm-hmm. But when you actually look at the real time scale, the time scale for these changes in CO2 and temperature, the typical time scale is of a significant change is 5 to 10,000 years. Whereas today, we have increased CO2 in 100 years by 40%, or 120 parts per million.
Right.
Like a geologic instant. It's like an explosion from a geologic perspective. And we're still going full speed. Gotcha. So it's very different from earlier natural climate fluctuations.
Now I need to ask you about Barrow and the Arctic, in the sense that even the earliest climate models that I can remember back in the 80s, at least when they became more public, indicated that the majority of the warming would occur in the Arctic, which is exactly what's happened. What is a simple, basic explanation for the general public in terms of why is the Arctic warming up so much more than everywhere else?
It probably has to do with reflectivity. So the Arctic is covered with a lot of with snow and ice. Especially snow varies tremendously with the seasons. And if it starts warming up and you have less snow on average and less sea ice on average, not in any particular spot, then the Arctic actually absorbs more solar radiation in the summer, especially. And so that is a positive feedback. So that creates more warmth in the Arctic and more melting. But still, these things are hard to predict.
Right.
Because we see now, at the moment, we have seen record loss of sea ice, floating sea ice in the Arctic. And this was not predicted by the models.
Right.
They did predict less sea ice, but not as dramatically as what actually happened. So this is an example of how difficult it is for models to make really a prediction other than, oh yeah, there will be less sea ice. They did not predict how fast it would go, and maybe it will stop now for 10 years, who knows. Of course, while we observe all this, we will also get tools to understand what is happening. Right. And that's the sad part, in a sense. So we can't make really good specific predictions about which areas are going to receive more rainfall and which less, etc., etc. So how it will affect people in certain places. So now I lost my train of thought.
You're fine.
Yeah. So there's not much we can do about it, but I'm confident that we will learn to understand how the climate system works in the long run as it unfolds. So as sea ice disappears and snow cover becomes less and ecosystems respond, then we will learn what the mechanisms are and how it really works. And then, of course, we've also won the argument by then. Here,
right.
Climate change, see, everybody can see it, but it's also too late. That's the sad part. As we learn how it really works, it's also too late to reverse it. There's thousands of scientists looking at this problem. If I could find a way to explain that we're all wrong, I would jump on it. That's a guaranteed Nobel Prize. And that's how science works. Now these contrarians that you talk about, you might say, no, the majority of the scientists will prevent such papers from being published. That's bullshit. If I or anybody writes a really well-argued paper that we have done some things wrong, it will be published. I'm very confident.
So
and there will be a controversy too, and it will rage for a while.
Right.
But that's how it works.
the peer review process is still
Yes.
reputable.
Yeah. So now I'm with NOAA, right?
Right.
I don't do temperature records, by the way, but I tell you what we do with our greenhouse gas data. All of our measurements are available to everyone on the web and also on request. But the web, you know, I prefer people just take it because we don't have time to respond to each individual.
Sure.
And we don't select these data. Everything is there. The data that we use to calculate trends, and also the data that we think data that do not represent large areas in the atmosphere that are noisy for some reason, it's all there. So we don't use those, but the data are there with a little note on it. Be careful with this. But people are free to use it if they want to.
Right.
So everything is transparent and documented. And I don't personally know the people in NOAA who maintain a temperature record, but I'm pretty sure they have the same philosophy about this.
Right.
If not, I would fault them for it. By the way, there were these three different groups who maintain a temperature record. There was the group at NASA, a group at NOAA, and in England. They all three had a global temperature record. Pretty much the same answer, but of course you could say also using pretty much the same data, not exactly. Slightly different methods and using maybe 90% of the same data. So a couple of years ago there was this scientist whom I know very well, Richard Muller, at the University of California in Berkeley. And he was going to do it all, he's going to do it just independent of everybody else. And he was also a climate skeptic, at least he proclaimed himself to be a climate skeptic. And he did indeed use a very different method. And guess what? He got the same answer.
Has he converted?
Well, he says, well, these temperature records, I agree with them. And he was skeptical. I mean, so he's a good scientist.
Right.
He wants to do his own analysis of it. And he gets the same answer. If he had gotten a different answer, of course, he would have loved that.
Right.
But regardless of that, he got the same answer as the other people, and he said so.
And so you are willing to be wrong if being wrong meant that we wouldn't be confronting this issue. I mean, in other words, you're not absolutely heck bent on keeping this conclusion. If something came along and changed your mind,
like I said, if I had some brainwave or some discovery that nobody had thought of it, that would nullify most of the worries that we have about climate change, I would rush. Not rush. I would be very careful. I would try to get all the evidence together, look at it in different ways, try to see what other consequences, if I was right, what other consequences there should be, and look for those. And if it seems to hold up, then go for it.
Right.
Yes.
And you might be introduced at the State of the Union address, you know, as a Nobel Prize.
I would probably stay away, but anyway.
Okay, all right.
It's calisthenics for the Congress, you know. Stand up, sit down, stand up, sit down. That's the only exercise. Yeah.
There are just a couple other things here real quick. The people that still make the argument that the sun is driving all this. It seemed like I had heard or read in a paper at some point that the smoking gun against that argument was that if the sun was driving it, both the stratosphere and the troposphere would both be warming.
Yes.
And that the troposphere is warming and the stratosphere is cooling.
Yes.
And so that pokes a big hole
That
in
is that is typical response to the greenhouse effect. Yes. The stratosphere is cooling. It's part of the greenhouse effect. Yes.
Okay.
So that is a big nail in the coffin of the solar theory, yes. But there are many variants of solar theories. There are probably still some others. There's another argument against the solar theory. Okay. People have been looking at the sun as a potential culprit, by the way, for many decades. And nobody has come up with something that is plausible so far. That's not a good track record, by the way, to take it seriously. But here's a very simple argument. We know from what the what the change in the energy budget of the Earth is, how much heat is retained, extra heat is retained from the extra greenhouse gases. Currently 2.9 watts per square meter over the entire Earth. What is the solar forcing compared to that? 5%.
Oh, okay.
Compared to that.
Okay.
So if you want to make the sun the driver of things, you need to come up with an amplification natural amplification mechanism.
Okay, I gotcha.
That amplifies the solar effect, and at the same time you have to explain away the known effect from the greenhouse gases. Nobody's done that, because when you come up with any mechanism that would amplify solar changes, you would also have to apply that to the distant past, and there's no evidence for that. The ice ages and the interglacials are in lockstep, more or less, with how the Earth rotates around the sun and how it tilts more or less and things like that, and the eccentricity of the orbit and all that. Right. That has nothing to do with solar output. It has everything to do with how much energy the Earth receives at high latitudes by season. So it's not even total solar radiation. No, it's relatively small changes by season in limited places. So, which to me sounds like there are some serious feedbacks going on here with the climate change to make the climate oscillate like that with such a minor change.
Right, right.
But it's not linked to solar variability, by the way. It's linked to the Earth.
So the variance in the solar output cannot explain the variances we've seen through climatic history. No. Why do you think, or do you have a theory on why this has become such a divisive issue and why people are so unwilling to consider the possibility that their current thought pattern may be flawed?
I'm not surprised, because the consequences of the climate change problem of accepting that it is real are social and political, I would say, and moral. I mean, in the end. So the way I look at it is, what we know is that we face a very serious risk that will hit our children and grandchildren more than it will hit us. So personally, I feel we have a moral obligation to try to leave a better Earth for future generations.
And that's not a cliche for you.
No. And climate change is one of many aspects, by the way, of all the things that we're doing. But it's also a political issue. And I can see that people might feel uncomfortable with that. Like, I'm responsible for myself. I'm free to do what I want. I don't want limitations put on my my space to do whatever I want. So that's quite fundamental. These are political issues. So I'm not surprised. What I do deplore is that the things that we know really well fall by the wayside, because it is irrational to ignore things that science really knows. It's irresponsible also for politicians to ignore that, to wish it away.